So using the same idea that we just used with circles, we are going to also look at that as the area underneath a curve. And we talked about this way back in section 1.1. We barely touched on it. We said, hey, we'll get to this later. Well, it's later. So notice if I have 4 rectangles trying to find the area underneath this curve from A to B, it leaves me with an undershot here and an undershot here, so a little bit less than what's correct at those 2 places, and then a little bit more here and here, but overall decent estimation. But if I were to then increase it to 8 rectangles, notice, yes, I still have some areas where this underestimates my result, and I still have some areas, whoops, where it overestimates my result. But you get the idea that if I then made it 100 rectangles or 1,000 rectangles, that it's going to get closer and closer and closer to the actual area underneath the curve. So essentially we're doing the exact same thing that we did before. We're saying, what if we found an underestimation and an upper estimation? So notice here on my first picture, I've got my f of x, and notice all of these rectangles are below, so this is an under representation of area. And this guy, I made all of the rectangles go up to the top of the figure. So again, this is an overestimation. So all of this is overestimation, all of this is underestimation, and somewhere in the middle is the true area of the region. And if I continue to make more and more rectangles, these 2 guys get closer and closer together, kind of like the squeeze theorem that we talked about before. We can find the actual true area of the region. We're going to take a look at an example here, and the example itself isn't super difficult, but if we're not super familiar with sigma notation, this might get a little bit tricky. So I'm going to try to go through this as quick or as slowly as I can, excuse me. So without looking at any of this stuff or any of this stuff, I really just want to focus for a minute on the 2 pictures that I have. So I've got this curve, and the curve is x squared plus 5. And I am trying to get an overestimate and an underestimate. So how do I do that? Well, on the overestimate, or the upper estimate, I'm looking at creating rectangles by looking at the left-hand side of the interval and drawing a line to the right. So that's the height, is looking at the left-hand side and drawing a line to the right, and that's going to be the height of each of these rectangles. Okay, so the height of my first guy is obviously 5, and then from there it's all based on whatever this value is. So notice I've got a total of 2. So it looks like this guy is 2/5, this guy is 4/5, this guy is 6/5, this guy is 8/5. You get the idea. So if I were doing this the long way, then the length, so obviously there's a rectangle, so the base of the rectangle would be 2/5, and that's for each of my 5 rectangles. Again, I'm doing this the really long way. And then the height of the first rectangle is 5, which was what happens if I take f of 0, because f of 0 would be 0 squared plus 5, which is 5. And then I would take f of 2/5, oops, because that was my next x value, so I'd plug in 2/5 and find that answer. And then I would take f of 4/5, and I would take f of 6/5, and I would take f of 8/5, and I would never take f of 2, because as you can see, that would mean I'm drawing a rectangle here where 2 meets. So that's not what I'm going to do. Now obviously this sucked, and that only gave me if I had 5 rectangles. What if I then changed it to 10 rectangles or 30 or 100? So that's where this sigma notation is going to come in. So let's work through this together. Notice on each of these, the width or base was 2/5. That's where this came in. And so again, what I did was I took the total length, which could really be found by taking b minus a. If this were a, this were b, you get the idea. Total length divided by the number of partitions. And in this case, that was 5 partitions. So 2 divided by 5. That's where this is from. So now let's look at the rest of this stuff. So I'm finding the summation as I goes from 1 to 5 of this. So essentially, this guy represents the base, which means f of this represents the height. And then, of course, this guy is saying find the sum of all of the rectangles with the base of the green and the height of the blue. So where did f of 2i minus 1 divided by 5 come from? Well, essentially, we're saying take f of 0. And so if I is 1, 1 minus 1 is 0. So take f of 0. So that'd be 2 times 0 over 5, which is 0. And then the next one, remember, was 2/5. And so if I take, moving from 1 to 2, 2 minus 1 is 1, so it would be 2/5. And then the next one would be, if I plugged in 3, so that would give me the 4/5. You get the idea. So this is essentially a way to find what number would go on the inside, and then we're taking f of that. Well, what's f? F is this function. So notice this guy from here all the way to here is, if I take 2i minus 1 over 5 and plug it in for x, that's what I end up with. Then essentially I just used my calculator to come up with an upper estimate, which is about 8.08. Now, I did the exact same thing on the lower side, and I'm not going to work through it step by step like I did for the first one, but notice I still used this because I still have the same base of my rectangle down here, still 2/5 each time. Now, the only thing that changed is because I'm using now the right side of my figure, then this is 2/5, so I'm never using 0, but I'm using 2/5 all the way up to, this time I am using 10/5 or 2, and so that's why this guy changed, is I don't have to take 1 away from I, I'm just using I. But all of those other steps are the same, and then of course I just used a calculator to determine the lower bound, which is 6.48. So I still don't know exactly what area is occurring underneath the curve, but I do know that it's between my two estimates. How could I get a better estimate? Well, don't use 5 triangles, use 10 or 100 or 1,000. Now, obviously using 10 or 100 or 1,000 is a real pain in the butt. So instead of starting out by plugging in a number like 5 and saying we have 5 rectangles, I'm going to start by plugging in a number like n and saying I have n rectangles, n subintervals. So again, I want to find the width of each rectangle. Just like I did before, I'm going to take b minus a and divide it by n. So we didn't have this formula before, but essentially we're saying delta x is take your upper bound minus your lower bound and divide it by the number of intervals. So if I'm going from 2 to 0, or 0 to 2, I'm going to take 2 minus 0 and divide it by n, which is 2n. So on the last one, remember, we had 2 divided by 5 because we had a total width of 2 because it went from 2 to 0. So I got 2, and then there were 5 intervals, and that's where the 2/5 came from. So now we're just basically making a formula out of it. So our formula says b minus a divided by n is delta x, and then the endpoints can be found by taking the starting position. So in our last one that was 0, so that made it really easy. We started at 0, and then we took I minus 1 of delta x, and then just I of delta x. Again, adding the a if the a wasn't 0. So on the left-hand side, that's where I came up with this guy. I took a, which was 0. I took I minus 1 times delta x, which was 2 over n. That's this guy up here, same guy. Multiplied it out to get this. And if you'll notice, on the last example that we just did, remember I said it was f of 2 times I minus 1 over n, and then I just plugged that in for f. That's exactly where that came from. The right-hand side started at 0, so I just took I times delta x, of course still being 2n, and that's where the 2i over n came from, and then I plugged that into my function. So essentially what I wanted to do is give you the general way that you would go about this. So this is always going to be delta x. This is always going to be the left-hand side, which may be an upper bound, maybe a lower bound, we don't know. And this is always going to be the right side. So these are formulas that you're going to want to know. So let's say I have a region bound by the graph of f of x equals x squared and the x-axis, and the vertical lines 0 and 2. So again, I'm going from 0 to 2, which means a is 0, b is 2. The width of each of my areas is 2 minus 0 over n, or 2 over n, and that's where this guy came from. And then using the left-hand endpoint, remember I said let's take a plus, and then it was I plus 1 delta x, oops, not a fraction, delta x. And so a was 0, so we didn't really care too much, and then I plus 1 times delta x would be I plus 1 times 2 over n, and that's where I got 2 times I plus 1 over n, this guy. That means that's what I'm plugging in to my function, so it's f of that. My function in this case, we changed the function, now we're dealing with x squared, so notice I'm just taking that value squared, still times 2 to the n, and again, notice this is a summation from 1 to n. And this one's a little different than the last one, because on the last one I had a number here, and here, and here, and so now I'm saying let's do this more generally for n, and then do some math magic, just do some simplification, and what I end up with is the summation of this. So what do I do now? Now is where those that simplification is going to come into play. This guy, just like before, is not going to change based on n. It's going to be whatever n is, but it's not based on I. So this is essentially a constant. So I'm moving this guy to the outside, and then I'm taking each of these three and making a separate summation out of it. So what's the point of that? Well, because I've got a formula for that summation, and I've got a formula for this summation, not the 2 stays on the outside, and then this is that constant that says take 1 times n, which is just n. And then it's just algebra, so then I'm just reducing, simplifying, etc., anything that I can, and obviously I've skipped several steps of that just because there's not enough room on a slide to show every single step that you would do. But of course I would distribute and then take that value and keep multiplying, so I'd FOIL it all out, take it times n, etc. Simplify as much as I can, and when I did that, this is what I came up with. And then I simplified just a little bit further, and this is the formula I came up with. So what's the advantage to what I just did as opposed to what I did when I had a 5 there? Well, this guy is more general, and I like general because if I have general, I can talk about finding the limit of this function, which is really the whole point, is so I don't have to continue to plug in numbers like 5 or 100 or 1,000. Now, I'm not going to go through this guy in as much detail, but this is the exact same thing using the right endpoint. So what did I do differently? This guy was 2i over n instead of 2 times the quantity of I plus 1 over n. But notice I did all of the same work and magically ended up at really the exact same function. So what did that do for me? I found, and again, the only difference here is this, I found that we have the same function, give or take, so 1 plus, 1 minus, and I know the area is between them. So now I can plug in a 10. I can plug in a 100. Eventually, I can use this to find a limit, and the limit, as I approach infinity, is going to end up being the actual area. So again, we're still just approximating. Eventually, we want to end up at the actual area.